Dear friends, in previous class we discussed about the multiplicative and complete multiplicative property of different arithmetic function, and we observed that the identity function is multiplicative as well as it is completely multiplicative, but the Mobius function is only multiplicative. Mobius function need not be completely multiplicative. Why? Because we know that what is mu of 4. Since 4 has a square prime factor, then mu of 4 equals 0. But what is mu of 2? Mu of 2 equals minus 1, and therefore mu of 2 into mu of 2, that is strictly differs from mu of 2 into 2, means mu of 4. Mu of 4. So by using this example, the Mobius function mu is not completely multiplicative, but it is multiplicative. Now we define the ordinary functions. Suppose the product of two functions, if g of x if it is defined as f of x into g of x, and their quotient function f by g of x equals f of x by g of x, provided g of x differs from 0. Under this definition, we can conclude this: even f and g are multiplicative, both this fg and f by g are multiplicative. So that's again immediate. Now, if f is, now we consider theorem, consider another result. If f and g are if f is multiplicative, then there's another result. If f is multiplicative, then f of 1 equals 0. F is multiplicative, then f of 1 equals 1. If f is multiplicative, then f of 1 equals 1. The result is important. How? Since f is multiplicative means f of mn equals f of m into f of n, provided m and n are relatively prime. F is multiplicative, not completely multiplicative. The given is f is multiplicative, means when m and n are relatively prime, f of mn equals f of m into f of n. Consider m. What is m? M can be rewritten as m into 1. So since m and 1 are relatively primes, then what is f of m into 1? Or f of m into 1 means equals, but since it is multiplicative, it is f of m into f of 1. That means f of m equals f of m into f of 1. That means f of 1 equals 1. So this is an important result. When a function, an arithmetic function is multiplicative, then when an arithmetic function f is multiplicative, then f of 1 is always equals 1. So by using this idea, immediately we can conclude that the man-dot function is not multiplicative. Why? What about the lambda is a man-dot function? What is lambda n? Lambda n is defined as it is log p whenever n equals some p power m and 0 otherwise. This is our definition. Agree? So what is lambda 1? We already proved that lambda 1 equals 0 means it differs from 1. Hence we can conclude that according to this result, the man-dot function is not multiplicative. Agree? Okay. Now consider another result. Consider another result. So there is a theorem. Given f, the theorem says that given f with f of 1 equals 1. F of 1 equals 1 means when f is multiplicative, we already proved that. When f is multiplicative, f of 1 equals 1. So the given conditions come to the theorem. The statement is in this way. When given f of 1 equals 1, then the first part is f is multiplicative. It is given f of 1 equals 1. Then the first fact is f is multiplicative f is multiplicative, implies and is implied by f of p1 power alpha 1 etc. into pr power alpha r equals f of p1 power alpha 1 into etc. into f of pr power alpha 1. This is the first result. When f of 1 equals 1, then f is multiplicative if and only if f of p1 power alpha 1 etc. pr power alpha r equals f of p1 power alpha 1 into etc. into f of pr power alpha 1 for all primes pi and all integers alpha I greater than or equals 1. How to prove this one? So, come to the necessary arguments. First, given, since f of 1 equals 1, we know that and f is multiplicative. F is multiplicative means clearly, since f of 1 equals 1, f is not identically equal to 0. And for any two positive integers m and n, since f is multiplicative with m and n are relatively prime, we know that by definition f of mn equals f of m into f of mn equals f of mn equals f of m into f of m. Now let p1 equals, let m equals, now consider letter m. Let m equals p1 power a1 or p1 power alpha 1, whatever may be, p1 power alpha 1, comma, n equals p2 power alpha 2, etc., pr power alpha. Clearly, this m and n are relatively primes, means they have no common factor other than 1. So m and n are relatively prime. So, since m and n are relatively prime, we know that f is multiplicative. Therefore, f of mn means f of p1 power alpha 1, etc. pr power alpha r equals f of m into, means p1 power alpha 1 into f of n. What is n? It starts from p2 power alpha 2, etc. pr power alpha. Okay. So, here similarly, f of p1 power alpha 1, etc. pr power alpha r equals that one. Then by using this argument, what about f of p2 power alpha 2, etc. into pr power alpha r? It can be rearranged as, it is f of p2 power alpha 2 into f of p3 power alpha 3 into etc. pr power alpha r. Then proceeding in the same line, immediately we can conclude that f of p1 power alpha 1, etc. into pr power alpha r equals f of p1 power alpha 1, etc. into f of pr power alpha r. So the necessary part is finished. Okay. Yes. What about its reverse inclusion? How to prove this reverse inclusion? Means it is given when for any primes p and for integers alpha I greater than or equals 1, it is given f of p1 power alpha 1, etc. pr power alpha r equals f of p1 power alpha 1, etc. into f of pr power alpha r. Now, given f of 1 equals 1, this is the hypothesis, f of 1 equals 1. And let m and n are positive integers. We have to show that f is multiplicative for let m and n are positive integers with they have GCD 1. They are relatively primes. Then therefore m equals product I ranges from 1 to r pi power alpha I. Pi power alpha I and n equals product j ranges from 1 to s qj power beta j. Where I and j, I ranges from 1 to r, j ranges from 1 to s such that pi differs from qj. For all I differs from j. Okay. For all I and j. For all I and j, pi differs from qj. We can choose m and n in such a way that they are relatively primes such that m is product pi power alpha I, n is product qj power beta j. So what is mn from here? What is mn? Mn means product I ranges from 1 to r pi power alpha I into product j ranges from 1 to s qj power beta j. Hence, Mn is given. So what about f of Mn? Then we have to show that f of Mn equals f of M into f of n. What is f of Mn? Starts from f of Mn. What is f of Mn? F of this product. Means it is f of that product means it is p1 power alpha 1 etc. into pr power alpha r into q1 power beta 1 etc. into qs power beta s. Okay. So that equals, come to the hypothesis. What's the assumption? F of p1 power alpha 1 etc. pr power alpha r equals f of p1 power alpha 1 into etc. So from here we can conclude that it is f of p1 power alpha 1 etc. into f of pr power alpha r into f of q1 power beta 1 into etc. into f of qs power beta s. That means that equals f of product I ranges from 1 to pi power alpha I into f of product j ranges from 1 to s qj power beta j. Okay, qj power beta. What about this one? This is nothing but f of m, and this is nothing but f of n. So clearly f of m equals mn equals f of m into f of n. Clearly f is multiplicative under f of 1 equals 1 with the m and n are relatively primes. Okay, so the theorem is finished. Means if f of 1 equals 1 and f is multiplicative if and only if f of product I ranges from 1 to pi power alpha equals yes product f of I ranges the product I ranges from 1 to pi power alpha. So that is the hence the result of product. Now again under the same condition, when f of 1 equals 1, f of 1 equals when f of 1 equals 1, if f is multiplicative, then f is completely multiplicative. F is multiplicative. In previous case only f is multiplicative. Here f of 1 equals 1 and f is multiplicative, then f is completely multiplicative. F is completely multiplicative if and only if f of p power alpha equals f of p all power alpha. F of p power alpha equals f of p power alpha equals f of p all power alpha for all primes p and integers alpha greater than or equals 1. How to prove this one? So, this proof is in this way. Come to the proof. First suppose that f is multiplicative. First suppose that f is multiplicative as well as f is completely multiplicative. F is multiplicative means f is not identically 0, and f is completely multiplicative means for any m and n, for any two integers f m and n, f of mn equals f of m into f of n. Since according to our hypothesis or according to our assumption, f is completely multiplicative. Now, what about f of p power alpha? F of p power alpha equals f of p into etc. p. How many times? Alpha times. That equals, since f is completely multiplicative, it is f of p into f of p alpha times, that is f of p all power alpha. So the necessary part is immediate. How to prove the sufficient argument? That is to prove f of p power alpha. When f of p power alpha equals f of p all power alpha, we have to show that f is completely multiplicative. When f is completely multiplicative, it is multiplicative. So, first we assume that f of p power alpha equals f of p all power alpha for integers alpha greater than or equals 1. Agree. Later, m and n are positive integers. M and n are positive integers. Then choose m is product I with respect to I, pi power alpha I, and n equals product with respect to j, qj power beta j. You can choose m and n in such a way that m is product pi power alpha I and n is product qj power beta j, where I ranges from 1 to r and j ranges from 1 to x. So what is f of m? F of this one is given, f of p power alpha equals f of p power alpha. What is f of m? F of m equals f of f of m equals f of p1 power alpha 1 etc. pr power alpha r, means their products. That equals since equals f of p1 power alpha 1 etc. into f of pr power alpha, since f is multiplicative. Given f of 1 equals 1 and f is multiplicative. This is the hypothesis. Now we have to show that when f of p power alpha is f of p power alpha, it is enough to show that f is completely multiplicative. Since f is multiplicative, f of m equals this one. Similarly, f of n. What is f of n? According to the same argument, f of n equals f of q1 power beta 1 etc. into f of qs power beta s. F of qs power beta s. Therefore, what is f of m into f of n? F of m into f of n equals, come to this product, that is product I ranges from 1 to f of pi power alpha I into product j ranges from 1 to s f of qj power beta j. Agree? But what is mn? Now we show that f of mn equals f of m into f of n. What is mn? Mn means these two products. Products I ranges from 1 to r, pi power alpha I into product j ranges from 1 to s, qj power beta j. So what is f of mn? F of this product. Okay, f of that product. Since f is, that is means f of this one, p1 power alpha 1 etc. into pr power alpha r into q1 power beta 1 etc. into qs power beta s. Since f is multiplicative, we know that it is f of p1 power alpha 1 into etc. f of pr power alpha r into f of q1 power beta 1 etc. f of qs power beta s. That means it is nothing but product I ranges from 1 to f of pi power alpha I into product j ranges from 1 to s f of qj power beta j. What about this one? That is f of m into f of n. If it is f of m into f of n from this result, this one. So clearly f of mn equals f of m into f of n. Thus, when f of p power alpha is f of p power alpha and f is multiplicative, then we can show that f is completely multiplicative. So this is the proof. Agree? Yes. Now, multiplicative functions and the Dirichlet multiplication. So, here if f and g are multiplicative, then we show that the product, Dirichlet product f star g is also multiplicative. If f and g are multiplicative, f and g are multiplicative means if m and n are relatively prime, f of mn is f of m into f of n, and the g of mn equals g of m into g of n. Now we have to show that f star g of mn equals, we have to show that f star g of mn equals f star g of m into f star g of n. Means h of mn equals h of m into hen, or where h equals f star g. That is the requirement. So how? So only for convenience, let h equals f star g. It is given f and g are multiplicative. Now what about since m and n are relatively prime with m and n are positive integers, with m and n are relatively prime, then what about h of mn? H of mn equals f star g of mn. Okay. Now by definition of this Dirichlet product, it is sigma over C divides Mn. C divides Mn. F of C into G of Mn by C. Agree? By the definition of Dirichlet product. F star G of Mn equals sigma over C divides Mn F of C into G of Mn by C. Now, every divisor C of Mn can be expressed in the form. Every divisor C of Mn can be expressed in the form C equals AB, such that A divides M and B divides M. A divides M and B divides N. Every divisor C of Mn can be expressed as the form C equals AB, such that A divides M and B divides M. Let's make it. Moreover, A and B are relatively primes. A divides M, B divides N. Then moreover, A and B are relatively primes. So since M and N are relatively primes, so clearly M by A and N by B are also relatively primes. Thus, there is a one-to-one correspondence between the set of products AB and the divisor C of Mn. There exists a one-to-one correspondence between the set of products AB and the divisor C of Mn. Hence, what about H of Mn? Therefore, H of Mn can be expressed as sigma C divides Mn means it is sigma over A divides M, B divides N. It is C means F of AB into G of Mn by C. Mn by C means Mn by A. That equals sigma over A divides M, sigma over A divides M, B divides N. Since F is multiplicative, it is F of A into F of B into, since G is multiplicative, it is G of M by A into G of N by B. So you can associate, you can rearrange it. That equals sigma over A divides M, F of A into G of M by A into sigma over B divides N, F of B into G of N by B. So that means it is H of Mn equals, what about this one? That is H of M into H of N. Hence, H is multiplicative. If M and N are relatively prime, then H of Mn equals H of M into H of N. That is, if F and G are multiplicative, then their Dirichlet product is also multiplicative. Okay.